Hi friends, as we all know, we are all are going through a very difficult time, and hope all are keeping well and doing good. In this situation, university has already declared vacation during from March middle to May 21st. So whatever modules remaining in our ATM2201 course will be taken in this video format, interactive video sessions, through interactive video sessions. So in this I will upload few video lectures, then I will give some assignments and some projects related to the topics. Based on that, basically I am going to evaluate at the end of the course. So in the regular class, though we have completed the module 1, module 2 and 3, part of module 2 and part of module 3, still I am starting from the module 1 because some of you might have missed those classes. But in one lecture I will briefly cover what we have discussed in module 1. So I slightly reoriented or rearranged or modified the course content little bit to suit for this video format. So let us begin with the first module, the scales of weather systems and map projections. So if you look at our course title, it is synoptic and tropical meteorology. Most of the students misunderstand that synoptic meteorology deals with synoptic scales of the weather systems, but it is not like that. Actually, synoptic meteorology deals with the entire synopsis of the weather systems or simultaneous view of the atmosphere over the globe. So that is the meaning of synoptic meteorology. So earlier, before numerical weather prediction systems and advanced forecasting systems came into existence, most of the weather prediction was mostly subjective based on the synoptic conditions. So regarding the scales of motions, for any type of weather systems, we have a dominant or a unique spatial and temporal scales associated with the weather systems. So that means they are interrelated. If spatial scale is more, according to scale analysis and all, the temporal scale should be also small. Like that, the spatial scale increases, naturally temporal scale also increases. So based on the for our convenience, but in the real atmosphere, all physical processes are interrelated. Like small scale process will interact with the large scale process. In essence, the large scale atmosphere trigger small scale process. So that means it is both way. The weather systems are both way interacted because it is a upscale transfer of energy taking place. At the same time, the large scale features provide the necessary energy, background energy for the small scale processes. So that means they are in essence not separable. Still, for our convenience, we classify the system for understanding the characteristics of the systems happening at each scale. So starting from the smaller scale, that is micro scale, which is of the order of few meters to few kilometers, maybe 1 kilometer, 2 kilometers. So which starts means the temporal scale is something of the order of few minutes. the turbulence, thermal plumes, all these processes comes under microscale processes. Then the mesoscale processes. Mesoscale process has a typical temporal and spatial scales associated with it. So typically a mesoscale process consists of spatial scales of the order of few kilometers, few maybe to 5 to 10 kilometer to up to 1000 kilometers. So it is a broader scale. So in that scale itself there are different type of characteristics regarding the weather systems. So based on the nature of the weather systems in this scale, the mesoscale process itself is further divided into three characteristic scales. It is basically for our convenience to understand and study the systems. So the mesoscale process further divided into meso beta, meso gamma, and meso alpha. Start with the meso gamma, then meso beta, and meso alpha. So that means meso alpha scale systems are spatial scales of the order of 200 to 1000 kilometers, and then meso beta comes under that, between something like of the order of 20 to 200 kilometers, and meso gamma scale is further less than 20 kilometers. If you consider the temporal scale, the meso gamma scale lasts for something like few minutes to few hours. Then meso beta scale systems last for maybe few hours, like 2 to 6 hours. Then meso alpha scale system slightly more, maybe they last for more than 6 hours to 12 hours, sometimes more than that. So then further coming to the synoptic scale systems, before that the typical example of mesoscale systems are the clouds, the thunderstorms, cloud clusters. All these weather systems comes under mesoscale process. The synoptic scale process is another dominant scale, which is of the order of few thousand kilometers, 1000 to maybe 5000 kilometers, 1000 to 5000 kilometers, the spatial scale. So maybe sometimes up to 10,000. The typical weather systems comes under synoptic scale systems are tropical cyclones, extratropical cyclones, frontal systems. They cover almost like more than 1000 kilometers in the spatial scale. They last for few days to weeks to up to 1 or maybe 10 days. So that means depending on the spatial scale, they last for maybe for more than 2 to 3 days to 5 days, sometimes a week or 10 days. So the typical example of synoptic scale systems are tropical cyclones. And then comes the planetary scale. Even though it is broadly classified as planetary scale, all the large scale wave activities, for example our monsoon systems, the monsoon system is considered the full monsoon system is considered as a planetary scale system. In the monsoon system we can find synoptic scales also. So broadly speaking, the South Asian monsoon system is a kind of planetary scale systems, and all jet streams comes under planetary scale systems, and that is of the order of 10,000s of kilometers, which cover more or less more than half of the globe. It will cover maybe 1/3 of the global scale. It will cover. And above that there are other scales like climate scales, decadal scales, and all. So these are the basically we will study up to planetary scale systems in this course. So coming to this, these are the brief features I already explained in the previous slides. But on the right side, I have given like um, nowcasting, short to medium range, subseasonal, seasonal, and decadal. The nowcasting is a kind of forecasting strategy used to predict mesoscale systems. So, which is nothing but thunderstorms, mesoscale cloud clusters. So, these are the system which the focus of nowcasting is to predict these type of systems. And another is the short to medium range system, where little bit higher on the meso beta to gamma scale system, like cloud clusters, score lines. All these systems we will learn later. And then short to medium range comes the tropical cyclones also comes in that scale. Subseasonal and seasonal scale, like large scale wave activity, seasonal cycles, El Nino southern oscillations, planetary waves, monsoon systems. All this comes under subseasonal to seasonal scale systems. And then naturally decadal scale and climate variability. So the first thing required for any kind of weather analysis is that we are getting data from each and every corner on the earth surface or from the atmosphere, but all this data has to be represented in the two-dimensional space, like in a map. So that means we need a map projection to represent the three-dimensional structure of the spheroid of the earth. So that means from three-dimensional we have to project all this into a two-dimensional paper. For that we need kind of map projections. So there are some desirable qualities for a map projections. These are either they have to preserve the angle on the flat surface and the sphere should be equivalent, or they have to preserve the area on the flat surface and sphere should be equivalent, or the preservation of the shape on the flat surface and sphere should be equivalent, or the correct cardinal direction on the flat surface and sphere should be same, equivalent, not same, equivalent. The preserving the shortest route, the shortest distance between two lines is a great circle. So these are some kind of desirable properties which needs to be kept in mind when we choose a map projection. So there are different types of map projections available. So in terms of their class, the class, which class they comes under, like cylindrical projection, conical projection, azimuthal projection. These are the different classes of the map projection. And then point of sequency. That means either it is tangent or secant to the point of intersection. And then the aspect, whether it is normal to the, that means perpendicular to the flat surface, or transverse or oblique. Then the distortion property, that means equivalent, equidistant or conformal. So that means if as a note I have given like no individual map projection can satisfy all 5 of these considerations which I have discussed in the previous slides. In meteorology, most important consideration is that angle to be preserved. This is important for the accurate representation of the wind fields, especially the kinematic fields. As I discussed, these are the different classes. That first is cylindrical, then conical, then azimuthal projections, then the property is normal, whether it is transverse or oblique, or then azimuthal projections, different kinds, mnemonic, stereographic, orthographic, azimuthal projections. If you look more closely, angle, as I said, in meteorology, the main property we look or we try to preserve is the angle. That is known as conformal projection, which is widely used for synoptic charts. They can be Lambert, Mercator, or polar stereographic projections. Though they do not preserve area or shape, their distortion is more over a specific latitude, and that means Even though Lambert projection, Mercator or polar stereographic projection, they preserve the angle, but they are suitable for specific latitudes. That is the important thing. They are suitable only for specific latitudes. Why it is so? Because if you consider a Mercator projections, so the Mercator projection, if you look at the South America and the Greenland, this is on the left side, it is on the spherical spheroid, and the right side projection on a Mercator map. So after projecting this spherical Earth to a Mercator projection, if you look after projecting, if you look at the size of South America and Greenland, which Greenland will looks like bigger than South America. In reality, it is 1/3 of the size of South America. So this is the kind of distortion happens. But if you choose Mercator projection for studying the mid-latitude systems or polar systems, so that means, but if you look at the equatorial region between 30 south to 30 north, you can find that both they preserve more or less same area both in the spherical Earth and also on the projected Mercator projection. So that means the Mercator projection inherently, which is mainly used for tropical weather analysis or lower latitudes. And then if you want to look at the mid-latitude weather systems, the Lambert conformal conical projections are the best, because in mid-latitude, if you take mid-latitude in the spherical Earth and in the projected Lambert conformal projection, the places which comes in the mid-latitude belt, that means above 30 degree to between 30 and 60 degree latitudes, either on the southern or northern hemisphere, the size, the area, there will be minimum distortion of the places comes between these two latitudes when we use a Lambert conformal projection. So that means this Lambert conformal projection is mostly used in the mid-latitude weather analysis. Another is the polar stereographic projections. The disadvantage of this is that we can at a time in this projection we can view only half of the hemisphere. That means if you want to look at the northern hemisphere weather systems or polar weather systems, northern hemispheric polar weather system, we have to use one projection is centered on the northern hemisphere or North Pole, and if you want to look at Antarctica, we have to use another the projection which is centered on the South Pole. So that is the polar. So basically, if you consider this, we have to look at the map scale factor. Map scale factor is nothing but the unit distance on the spherical Earth divided by unit distance on the projected surface. Should be, if a projection is a perfect projection, this map scale factor should be near to 1, close to 1. So that means there won't be much distortion. So both on the spherical Earth and the projection, the shape and area looks like similar. There will be minimum distortion. So that means, considering this, the Mercator, if you look at the map scale factor, Mercator projection map scale factor is close to 1 between 0 and 30 degree latitude. That means this projection is mostly useful for tropical weather analysis. After that, this is increasing. So that means if you go further, the places on the projected surface looks like bigger and bigger. So that means that is why Greenland looks double or three times the size as South America. So if you look at Lambert conformal projection, the scale factor is close to 1 between 30 and 60 degree latitudes. That means for mid-latitude weather analysis, we can use Lambert conformal projections. And if you look at the polar stereographic projections, there are different variants of the stereographic polar projections also. Azimuthal projections. Here it is polar stereographic projection. If you look at the scale factor, which is close to 1 between maybe between 70 and 90 degree, either on north or south latitudes. So this is regarding the basic qualities of a map projections. What are the qualities to be preserved when we choose a map projection, and how to choose a map projection for different latitudes. So these are the fundamental things regarding the map projections. So then all these data sets, like for weather analysis, we need at least minimum observations of few basic fields like pressure, temperature, humidity, wind, and maybe sometimes radiation or fluxes. So all these weather fields has to be prescribed on this two-dimensional space or on the projected surface, on a map projections. And after that we will analyze the synoptic view of the atmosphere at a particular time or particular instant. So that means maybe in observational techniques you have studied that at a regular interval we are taking observations. This is known as synoptic hours. It is either 0 UTC, 06 UTC every 6 hour interval, or 12 UTC and 18 UTC. In between also we sometimes take observation like every 3 hour interval. That is known as the 6 hour interval is known as main synoptic hour, and the 3 hour interval coming in between is known as auxiliary synoptic hours. So these are the kind of observations needed for synoptic analysis or weather analysis. Either they are surface observation, land-based or sea stations like ocean vessel, fixed weather ships and all. An upper air observation that comes from pilot balloon, radio wind observation, radio sonde observations. They consist of observation regarding temperature, humidity, wind at different levels, and satellite observation that is coming from both polar and geostationary satellites. Then aircraft observation, that is known as air observation, wind, temperature and pressure. Then reconnaissance flights, like sometimes flights will go inside the tropical cyclones and drop some kind of radio sonde is going up. Ravens means reconnaissance, that drop sonde is coming down from the aircraft. That will also measure during it when it is coming down through a cyclone. It will measure the pressure, temperature variation inside the cyclone. So that's also possible. And then the radar observations, that's basically used for nowcasting purposes. So these are the different type of observation platforms. Like we are getting different type of variety of observations coming from different spatial points and coming at different times. So that means there is no standardization of this observation. There are different type of observation. If you consider the quality of the observation, in situ observation like surface observation or with radio sonde observation, those are considered as the in situ observation. So where exactly they will go and measure. So that is kind of class 1 observation. So if you want to evaluate some other observation, basically compare as a ground truth, we compare with class 1 observation. That is nothing but surface observations and the radio sonde observations. And then another is class 2 observation, that is basically remote sensing observations from satellites, radars and other remote sensing methods. Another is class 3 observation. That is nothing but if you are estimating based on some indirect information. Like if you have a geostationary satellite which look at particular type of clouds over a time. So then between two instances, based on the position of the cloud or how far the cloud is moving. So between these two frames, we can roughly estimate the cloud motion vector or indirectly estimate the wind speed of that where that cloud presents. So that means that level wind speed can be indirectly estimated through this. So these are different kind of observation. All this observation together we have to analyze and make it into a standardized form for weather analysis. So that is a very complex process. So that may be in the 5th unit I will little bit cover how we will standardize this observation to make into a means similar platform, or in an optimal way how we will make use of combine all kind of this observation in a useful format. So that will little bit we will discuss in the 5th module. But these are the basic observation sets we basically use for studying weather features. So these are the on the left it is given in situ point observations. The spatial coverage of these point observations are very less. So for weather analysis we need to have as much as observation from each and every point on the Earth's surface and in the atmosphere. So that is not possible with in situ observation. There are limitations. That is why there are a lot of data gap if you only consider in situ observation. So in order to fill this gap, basically the satellite and radars will somehow do this job by filling the gap. But you have to remember that radar or satellite will not directly measure the actual value of temperature or pressure. We are estimating from indirectly through some other empirical relationship. So that means the quality of the observation, if you consider in situ observations are perfect, then satellite observation, that means if there is no other observation, we have to depend on satellite observations. If there is in situ observation, we will take in situ observations. Then the radar observations. Radar also, there are different types of radar. That also, maybe if time permits, we will discuss regarding this. There are different classes and different types of radars available. One which is having in our campus, the main campus, is stratosphere troposphere radar. That will not scan in the 360 degree. Instead, it will scan in the vertical. That is the only radar which measures the vertical velocity of the atmosphere. There is no other instrument which can directly measure the vertical velocity of the atmosphere. So that means if you look at another radar which is installed in the IMD campus in the Thokumpudi, that is a scanning radar. That is a Doppler weather radar. So that will scan. This on the right side, this is the antenna of the Doppler weather radar, typical antenna shape of a parabolic antenna of a Doppler weather radar, and bottom is the Doppler weather radar signal from a cyclonic storm. And then these radars can also be placed on satellites also, because there was a satellite known as TRMM, tropical rainfall measuring mission satellite. So that is ended in 2015. After that, the successor is like global precipitation measuring mission satellites. So they carry the radars on board satellites. So this is a typical radar images of a radar image from which is placed in a satellite. Then another type of CloudSat or Calypso type of another type of satellites also measure the vertical structure of the atmosphere. So these are regarding the radar observations. So this already I mentioned another GPS radio occultation observations. So then, considering I already told, observation is not perfect. There are three type of errors associated with observation. One is instrument error. If you take any instrument which is having some kind of error in its measurements, like accuracy or error, so that means instrument error is an inevitable part. And then error of representativeness. That means error occurs as a misrepresentation of smaller scale. So then is satellite, or if how exactly we represent the weather features over a particular region. So that is the error of representativeness. Then observer error. Sometimes the in situ observation is taken by observer. So sometimes he also make based on his subjective analysis. Even if there is a drastic sudden change in any parameter, like wind speed increase from 10 meter per second to 50 meters per second, or temperature increase from 30 degrees Celsius to 40 degrees Celsius, observer will think that this may be erroneous observation. He will adjust something. So that is kind of another way of source of error as far as observations is concerned. So this also we will discuss in the fifth module, where we mostly discuss about how all these heterogeneous observations coming from different places and coming at different times can be brought together to make a common to a common platform, to make a continuous analysis of the observation of the atmosphere, and from each and every point of the earth surface or the atmosphere. So there we will discuss little bit further there. And then if it's already I told, there are merits, advantages, disadvantages of both in situ observation. In situ observation is perfect, but it will not, as I have shown in the previous slides, that there are a lot of huge data gap. If you consider with the in situ data alone, we cannot survey. So we have to depend on satellite. That is basically the data gap we can fill through satellites. So these are different type of, if you take any one parameter, there are different observations which gives the same parameter. So we have to take which one is the better one to analyze a weather systems. So there are another tools which is commonly used for weather analysis are synoptic observations of meteorological parameters plotted on appropriate map projection charts. Mainly that is mean sea level chart, upper air chart, and auxiliary charts. Then satellite imageries, various derived products from satellites. Then nowadays different model outputs are being dynamical model, numerical weather prediction model outputs are being used for weather analysis. Then ships and buoy observations, weather radars, and then aircraft. In this COVID season, there are many reports coming that all aircraft flights are stopped, aircrafts are stopped. So that means there are plenty of aircraft flying each day, and they are also taking observation, giving back to meteorological community. That is known as air observations. So that also there will be plenty of aircraft flying at a given time. So now due to COVID, it is completely altered, so that the observation coming from aero is stopped, and this is actually affecting the quality of the weather prediction. There are reports regarding that. So that means any kind of observation can be used for weather analysis and forecast, but use it wisely. Thank you.